recording.
All right. So the focus activity is a lot simpler than those problems we just did on the homework. So we got a golfer starting at T. He hits the ball 220 meters to point A. You want to know how off he was, because hopefully he was aiming at point G. You want to know this angle T, how many degrees off he was on his shot. So what law can we use to find this angle T? Law of cosines. What would that look like if we're keeping the variables in the equation? How would I write that out? Nice. Cosine. Nice. And then if we rearrange it for T, what would that look like? Still with the variables in it. Yep, just like that. And then, sorry? Nice. Thank you. And then we can just plug that in to the calculator. So, inverse cosine of, what were the numbers that we used? Minus 220 squared. All right. Over -2 times 220 times 340. So 23.8975, we'll round that to the nearest degree. 24 degrees. Pretty simple, right? Lose anybody along the way? All right. Oh yeah, center. Good? Everyone okay with it? Sweet.
All right. Well, before we get on with our next lesson, for the next couple lessons, we're going to be looking at how to graph sine, cosine, and then ultimately the other trig functions as well. Don't forget, tomorrow you have yourself a quiz over the law of sines and cosines. Very similar to the homework. I've just given you a couple of word problems, so I'm not thinking it's going to be anything too difficult. We're still 2 weeks out from this, but I want to go ahead and make you aware of it. Your second exam is going to be on Thursday the 21st. That's the Thursday right before we get out for Thanksgiving break. I think that's the best way to end that week. We come in on Friday, answer any questions you may have, and then we go spend some time with our families and friends. For this week, tomorrow by noon, if it applies to anybody, if you're needing a waiver for an upper-level course, okay, for the second 6 weeks, those waivers are going to be due to Mr. Young's secretary by noon tomorrow. All right, so if that applies to you. Okay. And if you also get the homework into me by the end of the day, you can still get the points for the point bank. It's the first assignment of the grading period. Okay. Well, let's get going. The graphs of sine and cosine functions are periodic. Oh, it's on. Okay, so they're periodic. This means that the function values will repeat as x increases. The sine value of a function is equal to the y value at the corresponding point or angle on the unit circle. Also, the cosine value is equal to the x value at this same point or angle. So we're still using the same idea. In fact, you're going to notice, my baby. Okay, we're going to notice that what we've been doing on the unit circle is going to directly link to what we're now doing here. So let's see what sine looks like. Since the graph will complete one full cycle on the interval from 0 to 2 pi, the period of sine is 2 pi. Now here's the thing, our ultimate goal, we're going to want to take the transformations that we looked at in here near the beginning of the school year and what you taught in Algebra 2, we want to apply those to the trig functions. So I'm talking about your dilations, lines, your reflections, your shifts. Ultimately, we want to go ahead and get to graphs like this. A times the sine of bx plus or minus c and then plus d. Okay, but first we need to know what the parent functions are going to look like. So let's start with the basics. We're going to be using 5 key points from each graph to help us out. Now for sine, we're going to go ahead and start with a 0. Okay, so sine starts with a 0, and then we have its first maximum, then we have another 0, we have a minimum, and then we're back to a 0 again. Okay, now when we say that sine has this particular period, well, you're going to see this particular graph repeat over and over again. So to completely repeat itself, it's going to need 2 pi radians. So you'll notice we ended at 2 pi. So 2 pi plus 2 pi would be 4 pi. So if we get all the way down here at 4 pi, it should complete one more cycle, or what we call another period. And this is just going to continue over and over. I can continue in the positive direction, but I can also continue in the negative. Okay. So as we go through this graph, yes, ma'am. I did print more of the papers. I'm sorry. Who did not get one the other day? Holy crap. Okay. So here we go. Would you pass one to her? I even made some extra copies this morning, anticipating that. Okay. And there we go. I'm glad you said something for an end. I completely forgot about that. Clarissa, would you pass it? Okay. Who else am I missing? Laura needs one. Okay. Jake needs one. Anybody else? Okay, good. So hopefully that information that you were copying down the other day, this one right here, like the first thing we have is that the domain is all reals. Okay. Well, looking at the graph, I mean, he does extend forever in both directions, but why is this? How does it connect to the unit circle? Okay, so to answer that question, let me go ahead and kind of bring up another question. Why do you think it repeats every 2 pi radians? Okay, what's that, man? That's one revolution on the unit circle. That's exactly right. If we go ahead and start here in standard position, if I were to rotate one revolution counterclockwise, that's one period of the graph. So if I were to rotate a second time, well, that's a second period. And how many times can I rotate? I can rotate an infinite number of times. That's why I can just continue to go forever in both directions. I could also rotate clockwise, which is going to go ahead and give me the same pattern going in the opposite direction that we saw. Now, let's go ahead and focus on those points for just a second. For sine, we do need to have these committed to memory. We started with a 0. Then we went to a maximum. Then we're back at a 0. Then we have our first what? Minimum. And now we're back to a 0 again. In fact, let's go ahead and identify those points. What you're going to notice as we go through, it's going to be graphed the same way as your coordinate pairs, your x comma y. But in this case here, the x value is going to be your angle measure. Now, it could be in degrees or radians. Here, we're going to be dealing with radians. But the y value, the output, is going to be the ratio of the two sides of the triangle. The only exception to that being if you're a quadrantal, if it stops on the x-axis. So let's go ahead and do this. The first ordered pair, this 0, is located at 0, 0. Okay. What would the coordinate of that maximum be right there? What radian measure did I use? Yeah, I went to pi over 2, and that'll give me what output? Okay, 1. So this right here, whoop, took that off as well. So this ordered pair right here is pi over 2, comma 1. So what's this third order pair that we're calling the next 0? What's the radian measure we have there? Pi, and then we have 0. Okay. So what's the ordered pair of that first minimum? So we got to 3 pi over 2, negative 1. And then we get back to our last 0, which should have 2 pi 0. Okay. In fact, take a look at those 5 ordered pairs. If you now go ahead and look at the bottom of your page, those are the exact key points that we listed on Tuesday. These are the points that we're going to go ahead and use when we start transforming these functions. Today is just the basics. We're just going to go ahead and start talking about, why the graph looks the way it does. So as we rotate around, okay, let's see here. Why do we have these particular ordered pairs? Well, remember, you're plugging the angle measures into sine in this particular instance, right? Think back, what does sine represent? Is it the x or the y variable? It's the y. So for example, if I were to take the sine function, if I plugged in 0 radians, okay, so at 0 radians, we have this ordered pair right here. Well, what's the y value? 0. So see, there's my angle input. There's the output. Now, this isn't the ratio of 2 sides because it's a quadrantal, but you're getting the idea. So this would give me the ordered pair 0, 0. And let's rotate around to the very next point, the one we're calling the maximum. If I were to say, okay, I've got my sine function, and I want to evaluate him at pi over 2. Well, here's pi over 2. Here's the corresponding value. What's the y value? 1. So if I input pi over 2 radians, my output is 1, according to the unit circle.
Teacher sports interruption. Freshman girls basketball. Your morning practice tomorrow will start at 8:05. Again, freshman girls basketball. Your morning practice tomorrow will start at 8:05. Thank you.
Okay. And so you can continue that all the way around. For the next 0, we had pi. So if I look at pi, what's the y value at that location? 0. But remember, these graphs are continuous. So it's not just these main degree measures and radian measures that we're looking at. It's any of them. In fact, let's take a look at one that we didn't go ahead and graph. What's halfway between 0 and pi over 2? What would this be right here? That's pi over 4, right? Okay. So if I go ahead and evaluate sine at pi over 4 radians, okay, well, here's pi over 4. There's the ordered pair. Well, what's the output? What's the ratio of the 2 sides? It's square root of 2 over 2. So if I use the same idea, an ordered pair, a point on this graph should be pi over 4 and square root of 2 over 2. Well, let's go ahead and see what that is. Okay, I've already got it typed in from the previous class. So square root of 2 over 2, let's say roughly is a 0.71. So if I were to come over here to my function, if it'll let me come down, at pi over 4, if I go straight up until I hit the graph and then right over, that location right there would be the ordered pair that we just found. Okay. Is everybody okay? Is this making sense with how we're getting the graph that we do? Okay. Even think about why it's bounded now. The range says the maximum value I can get is a positive 1. The minimum value has got to be a negative 1. Well, think about that unit circle. Okay. If I go ahead and look at this unit circle, the maximum value for sine is going to be at multiples of pi over 2. The minimum value for sine, negative 1, is going to be found at multiples of 3 pi over 2. So as I continue to rotate, I'm going to hit maximum, minimum, there's 1 period. Maximum, minimum, there's 1 period, just over and over again. Okay. In fact, what was that period? How many radians does it need in order to repeat itself? It's always 2 pi radians. This is the parent. So if I were to start here at this minimum, which is located at negative pi over 2, negative 1, before I can get to the very next minimum, I have to go 2 pi radians. Okay. Same thing here. If I'm going to go from a maximum to the very next maximum, I got to go 2 pi radians. Okay. Any questions on the graph of sine itself? Okay. Now, I know that some people the other day were kind of confused by the notation that I had here, so let me see if I can help you out. Look at the x-intercepts. You see how it says pi times k comma 0? What that's telling you is that you're going to have an x-intercept in multiples of pi. So what is an integer? Well, I'll go back over here and start to write this out. What's an integer? Okay, so definitely no fractions, no decimals. Okay. All right. So can anybody give me a little more about that? What kind of numbers are going to be in the set of integers? There you go. So positive whole numbers, their opposites, and what? 0. So the set of integers is going to look like this. You have -2, -1, 0, 1, 2, dot, dot, dot. Okay. Well, those are the values of k that we're using here. So why don't we just go ahead and start plugging in some ordered pairs? Like, for example, if k is -2, what's -2 times pi? -2 times pi. Now, don't worry about the 3.14 just in terms of pi. It's just -2 pi, right? So there should be an x-intercept at -2 pi, 0. Well, what if k equals -1? I'm just going right down the line. Then that would be -pi, 0. Okay, which I can actually see right here. I had just enough room on my graph to get it. Well, now what's the next integer? 0. So what's pi times 0? 0, 0. There's the origin. And you can just keep going. 1 times pi would be pi, and there's the second 0 that we got. Okay. So what you copied the other day, that's the notation that's going to help you find the location of any characteristic you want on the graph. Okay. Is this making a little more sense now? Okay. The only thing I do want to go ahead and bring up in addition to this, something is trending right now. That's awesome. The symmetry. What does it mean it's symmetric with the origin? What does that mean? Okay. Well, graphically, what can I do and know that this has symmetry with the origin? What did we talk about at the beginning of the school year? Andrew said that louder?
Rotate it 180.
If you can take the graph and rotate it 180 degrees. So if I were to spin it, okay, around this origin 0, 0, I'm going to get the exact same graph. Do you remember what our test was algebraically? We took f of -x if it gave me what? Negative f of x. So see, that's why we took the time to review a lot of these previous concepts, okay? Because now we're going to go ahead and start applying them to our trig functions. If we know that sine is odd, I should be able to apply this rule to sine itself. And this is one of our identities coming up. If I were to say sine of -x, what do you think that should equal? It will equal negative sine of x. The identities is something that we're going to dive into right before Christmas. It may even take us a little into January to get that done. Okay. But any questions on the characteristics of sine? How we get the points? Is anybody confused by anything? Okay. All right, well, let's go ahead and try cosine. Now, cosine is going to be very similar. Now, for sine, remember, what was the pattern? Did sine begin with a maximum, 0, or a minimum? Okay, so I heard some different answers. Sine starts with a 0, then has a what? Maximum, 0, minimum, 0. Remember, those 5 key points are what we're going to use when we get to the transformations. Cosine is going to follow the same pattern, but he doesn't start with a 0. He's going to start with a maximum. Then he has his first 0, then a minimum, a 0, and a maximum. So while sine repeated this shape over and over and over again, cosine's just a little different. I like to refer to this as the curvy V, because that's exactly what it looks like. That's going to repeat for cosine over and over again. That represents one period. And again, why do you think it takes 2 pi radians before the graph can repeat? Because 2 pi radians represents one what? One revolution. There we go. So if I go around one revolution, there's one period of the graph. If I were to go around a second revolution, there's a second period of the graph. And for however many times I rotate, I'm going to have another section of the graph. And I can also rotate clockwise. So I would have something like that, just repeating over and over again. Okay, so you're going to notice a lot of the same ideas. Because you can rotate an infinite number of times, well, the domain is all reals. Okay, what's the maximum value that cosine can get? 1. What's the minimum value? -1. See, it doesn't go to positive or negative infinity. That's why it's bounded above and below. But it's a little different for cosine. Remember, while sine was the y value, cosine is the what? The x value. So if I'm looking at all of these ordered pairs, the largest x value I can have anywhere is the 1. The smallest value is going to be found here. So as I rotate, again, I start with a maximum. Okay. Oops, I don't know why I put max there. That's a minimum. Sorry. Minimum, maximum, minimum, maximum, and it just keeps going over and over again. In fact, let's go ahead and identify those points. This is a max. Then we have a 0. Then we have a minimum. Then we have another 0. And we finish with a max. Okay. So what's the ordered pair of that first max value? Yeah, 0 radians, because this is the intersection of the x and the y axes. So at 0 radians, you should get an output value of 1. And that makes sense, because if you're looking on the unit circle, here's 0 radians, and the x value right there is 1. Okay, and it's the same idea. You're getting the ordered pairs as you rotate through. So what's the next 0? What's the location of this ordered pair right here? There you go. That is pi over 2, 0. Okay. Andrew, what's the minimum we have? Okay. So all we're doing, think about it as like an XY ordered pair. So I want to get from the origin, this point right here, and I want to get to this point. I want to know its coordinates. Now, this time, the input is radian measures, while the output is going to be the ratio of the sides of a triangle. So I'm going to start here. How far right, then down did I have to go? It's exactly right. Okay. So this right here would be pi -1. Because if I were to take cosine, if I plug pi into it, it should give me -1. And we see that right on the unit circle. See, here's pi radians that I rotated. There's the ordered pair. The x is -1. So we're taking the idea that we've been working on for several weeks now, and we're just turning them into coordinates so we can see the graph of this function. Okay. What's this one right here, the second 0? 3 pi over 2 radians will give me what? 0. And again, okay, look over here. If I were to rotate all the way around 3 pi over 2, here's the ordered pair. What's the x value? 0. That's all we're doing is evaluating the trig function as we rotate. Is everybody okay with this? Okay. What's our last ordered pair here? Okay, so this would be 2 pi and 1. So look at those 5 ordered pairs. Max, 0 min, 0 max. Now look at the bottom of the paper that we copied the other day. Those are the key points we're going to use for cosine. Okay. Now the notation is very similar to what we had before. Here the x-intercepts are going to be pi over 2 plus pi k 0, where k is an integer. Would anybody like me to go ahead and plug in and show you how we get those? You want to do that? Okay. So let's try a few. Pi over 2 plus pi k 0. Okay. So pi over 2 plus pi times k comma 0. Now these are going to give you the location of all your x-intercepts. K is an integer. Or remember, what were the integers again? Yeah. So we had 0, let me go ahead and start with the negatives. -2, -1, 0, 1, 2, dot, dot, dot. Okay. Now let's go ahead and start with some that we already see on the graph. Like how about this guy right here? Okay. Well, I'm going to find him when k is equal to 0. Because think about it, what would pi over 2 plus pi times 0 be? Yeah, that's just pi over 2, 0. Now let's move to the next integer, which is 1. So I'm going to go ahead and say pi over 2 plus pi times 1, comma 0. Well, now we just need to go ahead and take pi over 2 and add pi. Well, let's see here. Pi over 2 plus, we need a common denominator. So is everybody okay with that being 2 pi over 2? Because what's 2 divided by 2? 1, so there's your 1 pi. Okay. Well, what's pi over 2 plus 2 pi over 2? How many pi's would I have? 3 pi over 2, comma 0, which is the very next x-intercept. Okay. That's what these are doing. They'll be able to let you find any maximum, any x-intercept, or any minimum that you want. Okay. The only other thing I want to go ahead and bring up is what I did similar to the other one. This one isn't symmetric with the origin. It's not odd. Cosine, it's even. That means he's symmetrical with the y-axis. What does that mean? So I'm looking at this graph. What does that mean he's symmetric with the y-axis? What's that? Across what? There you go. If I could actually fold this paper, the two parts should come together perfectly. Does anybody remember what the rule was algebraically? If it's even, f of negative x should equal what? F of x. Remember, you should be able to plug in a negative x, and it simplifies to the original function. Okay, so since I know cosine is even, that rule applies to him. So I can say that cosine of negative x should equal what? Should just be cosine of x. Yet another one of the identities that we're going to be looking at come close to Christmas. Hopefully by mid-December we'll be there. Okay. Is anybody confused? Okay, Andrew, you said you were confused a moment ago. Are you feeling better?
Yes.
Is there anybody who's not understanding where we're getting the ordered pairs on either of these graphs? How are we doing? Okay. Well, that is as far as the other classes got today, so we will stop there. And we'll do our first transformations tomorrow when we come in. Okay, so don't forget, if you don't have the homework quite ready, as long as you get it to me by the end of the day, you'll still be eligible for what? The point bank. There we go. Still be eligible for that point bank. Okay.